guess so, yes.
Mm-hmm. So how it was there in Kharkiv, guys?
People are still breathing.
It's nothing new, I guess, and I guess this quarantine must be over.
Well, to be honest, I don't go to streets right now. It's been 3 days I didn't go out.
Oh, really?
I don't have anything to do. And this guy from motorcycle, he's still sleeping me.
Oh. So,
Yeah.
to be honest, Ali, I guess you will gain the weight.
Now in Ramadan, I don't think so.
Yep.
I don't think
So it's for me, it is hard. So today, Ali will be with us and hold this lecture. Ali, there's a question for you that Anastasia was asked by me. From where did you know me?
Should I tell all of people?
Yep.
Okay, then.
We're going to start to be more social.
So then did they start sharing, or let's say recording the conversation?
No. Yes,
Okay.
it's recording.
Wait. Should we wait or we can start now?
No, you can start now. So good luck, Ali. You have no more than 1 hour 45 minutes, but I guess it will take you less.
It will take less, yes.
Okay, so let us start it.
Okay, so now do you see the screen?
Yes, we do.
Everything is normal, Ali. You can make the full screen presentation.
Okay, right now.
Yep.
Yes, but what? So let's start. My name is Алі Чкеїр. In case you don't know, I'm a PhD student in Kharkov Polytechnic Institute. And I took my master degree last year in December. And like what Mikhailo told me now, I have to tell you how I met Mikhailo. So let's, I guess, go back to 2017. It was in February. We had the second semester, or even 2016. We had our second semester, and somehow we saw our new professor, or let's say a teacher, who was wearing an orange pants. Yes, an orange pants. So it's very unique, let's say. And it was the first time I saw Mr. Mikhailo Bratach, and he gave us oil and gas processing lectures. And from that time, we became more friends. And we had so much journey across Ukraine on motorcycle in Kharkiv, in Lviv, in Stary Saltov, in Odessa, and in Ivano-Frankivsk also. So yes, it started with the orange pants. Mikhailo knows about the orange pants. So let's move on. And today our lecture, we will talk about the prediction of liquid loading. I don't know what they put on the title in the Facebook, but today it's prediction of liquid loading, and we will talk about turners. So let's start. First, let's start with the stages of production. I guess my colleagues, they talked about the stages of production already, but we will mention it briefly. So we have 3 stages of production: primary, secondary, and tertiary. So in primary production, we have when the reservoir energy is enough to lift up the liquid droplets. What do I mean by this? We don't need any artificial lift methods because we have enough energy, reservoir energy. We have here the pressure, and the velocity is also high enough to lift up the liquid. While in the secondary production, during the lifetime of oil and gas, or let's say gas and gas condensate fields, because today we're dealing with the gas condensate fields, the pressure starts to drop. So in the secondary production, we will have something called pressure maintenance. What do I mean by pressure maintenance? I remember from last week, my colleague talked about pressure maintenance, and he talked in a specific way about water flooding, the injection of water. So in order to increase the reservoir energy. And moving on to the final one, it is a tertiary production. It is the last stage of the production when the reservoir energy is not enough and starts to decrease. So we'll talk more in details what happened in the tertiary production. So It's well known that over the life, or let's start with this on the right side, we have the typical gas well decline curve along with the indication of liquid loading. So we have the green field, gas velocity is enough to lift the droplet of liquid, and we have the brown fields after some time. So we have two graphs, if you see the expected and the indication of the liquid loading. So it's well known that over the life of a typical gas well, the gas flow rate will eventually start to decrease, like we stated, since the gas and from conventional gas and gas condensate is usually accompanied by water and liquid hydrocarbon. So the dropping of this gas flow rates leads to a corresponding declination in gas velocity below the level needed to hold up the liquid droplet. So in this period, it starts to be considered as the starting point when liquid starts to create an accumulation at the bottom hole. So in the final stage of this development, this liquid accumulation influence on the gas production from the reservoir, creating an additional hydrostatic pressure. This hydrostatic pressure, it also creates, or let's say adds, or by pressing on the bottom hole pressure, by raising it also at this nodal point. So hence, we will witness something called a decretion in the drawdown. What is a drawdown? Drawdown is usually the difference between the reservoir pressure and the pressure at the bottom hole. So this drawdown is basically the main one that is responsible for the liquid, for the recovery of gas and oil. So when we have a decrease in the drawdown, hence it will lead to something called stopping of the gas, or the gas will cease, the well will cease to produce. So such well have to be submitted to something called liquid unloading method in order to overcome this problem. So here, let us try somehow to relate, or let's somehow try to combine the liquid loading problems with the with the flow patterns. Okay, so during vertical upflow, due to the density difference, it is expected that the gas will flow faster than the liquid because the densities are different gas from the liquid. So depending on their velocity, the gas and liquid will present different topological distribution inside the pipe known as flow patterns. So these flow, let's talk more about these flow patterns. So what do we have here? If you can see, we have in the slide. So at high gas velocities, this gas tends to move to the center of the pipe, like we see here, of the pipe, forming a vortex commonly known as a gas core. So this liquid is then pushed out of the glass core and into the pipe, forming a film. Here, as we can see here, alongside the boundaries of the pipe, we have the film. This water is attached somehow to the pipe, and also due to the high shear at the gas liquid film interference, the liquid film is constantly atomized as droplets are transported in the gas core, while some deposit back into the film. So this flow pattern is usually called annular mist. When we're dealing with film, it's called annular mist. So, and this one is responsible, or it is preferred in gas well that produces liquid. So over the time, like we stated before, the gas velocity starts to decrease. So since the gas velocity starts to decrease, the liquid film starts to bridge the gas core, and the liquid close to the pipe well starts to fall back. So this leads to a new flow pattern, such as here, churn, slug, and bubble flow. And this bubble flow, it is the lowest gas velocity. So when we are dealing with the lowest gas velocity, so this amount of liquid per pipe section alongside the well is known as the liquid hold up. Okay, liquid hold up, and varies depending on the flow pattern.
Hello.
Please, can you turn off your microphones? So this also has an impact on the pressure losses, which have to be properly estimated alongside the well. So over the time, an increasing pressure presence of the liquid will be what created here at the sand face zone that generates an excess pressure at the sand face that can hinders, or if it's high enough, the gas stop the gas production. So this is commonly known as the liquid loading. Yes, do you still hear me, right?
Yes, all good.
Yes. So here we talked about the liquid holdup and the gas velocities alongside what? The flow patterns. So in a few words, let's say in a few simple words, first we will be dealing with something called annular mist when we have a high velocity. And then by the decreasing of the velocity, we will start to witness something called churn and slug, and finally bubble flow when we start to witness liquid accumulation. And here also we can see that the gas velocity also is decreasing alongside the depth also and the time, and the liquid holdup is also increasing. So let's move on further to start to talking about the models for predicting liquid loading. So here in this slide we can see the table of the list of models for the prediction liquid unloading. And we will talk today briefly about Turner's model, the most common one, about Coleman model, about Nossier and Lee. So these are four of them we will discuss it today. So the well for liquid unloading and gas lift method will be chosen usually by the comparison of actual gas rate and the minimum allowable gas rate for liquid unloading using one of these models like we stated for. So let's go further and let us start to talk about the critical velocity, because you will hear a lot about this critical velocity in this presentation. So what is critical velocity? This critical velocity is a method presented to predict the onset of liquid loading. So what do I mean by this? If you can see on the slide, the picture, we have the drag and the gravity and the gases velocity, let's say, the gases particle and liquid particle inside the vertical gas well. So the droplet of this liquid in here he took it in the case of annual flow pattern, if you remember. So inside the gas will be affected by two forces. The weight acts downwards. What do he mean by the weight acts downwards? He means by the gravity, and the drag forces from the gas act upwards. So here we have a drag force, he meant by bottom hole pressure, and the gravity act downwards. So when the drag force is usually equal to the weight, the gas velocity is at critical. So theoretically, at the critical velocity, the droplet will be suspended in the gas stream, moving neither upwards or downwards. So what do we have to do, or what should we do? Below this critical velocity, the droplets fall and liquid accumulates in the wellbore. So the critical velocity is generally defined as the minimum gas flow for prediction required for moving droplets upwards. So here, the critical velocity will play a critical role play in our presentation, and in order to predict whether we have liquid unloading problems or not. So let's move further. And in general, we cannot talk about liquid loading and the liquid accumulation without mentioning Turner's, because Turner's was the co-founder, let's say, for these models for prediction of liquid loading, and he is the common used model all around the world. So Turner's assumed that the droplet in gas wells are spherical and derived continuous liquid carrying critical gas velocity formulas. So in order to make calculation convenient, he took into account a drag coefficient was taken by 0.44. So we will talk also a lot, we will mention a lot the drag coefficient. So in case you don't know what is drag coefficient, it is a dimensionless quantity that is used to quantify the drag or the resistance of an object in a fluid movement, such as in air or in water, okay? So this, he took into account the drag coefficient as 0.44. So in order to fit his experimental data, he calculated the result, and the result were improved by 20% upward. So depending on the force balance, one applied to a drop, one can estimate or forecast either the liquid drop will lift up due to the force of the bottom hole, like we stated before, or it will settle down at the wellbore by the force of gravity. And here you can see on the right side on the upper right side of the slide, you can see the liquid droplets. We have the force of gravity, and also we have the drag forces. So also he investigated a meaning of critical gas velocity, which we mentioned earlier, which means that above critical value, any actual gas velocity will be able to lift up, while below this critical value, the drop of liquid won't be able to lift up, and it will end up settling down, forming accumulation at the bottom hole. Okay, this is what Turner's stated. And here you can see also on the down part from the right, you can see the velocity of the gas, of the condensate, here also the equations, and the velocity of the water, and the Q, the flow rate critical. So here, if you want, if you lay your eyes on the gas condensate velocity, you can see here 0.24, and also for the water 5.26. What do I mean by this? This coefficient is usually derived from the interfacial tension equations, and 45 is a density, and 0.0031 also is considered as a density, and the pressure, it's a wellhead pressure. And the flow rate, the critical flow rate, is a function of pressure, velocity, and the area over the temperature and supercompressibility factor. So this is what Turner's discussed and developed. Guys, if you have any questions, feel free to interrupt me and use your microphone in order to ask me at any time, okay? Because I cannot see your messages right now. If someone has to. Okay, one of you guys sending me the screen is being blocked by something. Guys, do you see the screen well?
There's something saying you should remove something blocking the slide. So like it keeps like blocking the formulas and other information on the slide.
Only for you or for all others?
For me as well.
You mean this? Wait, let us change the place. What about now?
It still appeared. It's like, please move the window, like in the middle exactly of your presentation. There's
Yes,
window.
I understand, but I'm away from this window. I don't know what should I do, but for me, I can see it clearly. So let us continue, because I cannot do anything about it. So here we discussed about Turner's, like I said, and let us move on to talk about Coleman, because he's the second one and it is the most common one used model. So let's talk about Coleman's approach. He presented 4 series papers, and he proposed model for predicting the liquid accumulation that is found, that its foundation was based on Turner's model without the 20% upward adjustment, but he provided no explanation for why this may occur. So this approach requires a less flow rate to be critical when analyzing data for a lower wellhead pressure, and it showed a promising results in which in wells which have less than 500 psi pressures. Okay, and he also had his own let's say formula or equation, but these equations are the same as Turner's. If you can see here, the only difference here is that by the deduction of 20%, so 3.369 for the gas, for the velocity of the condensate, and 4.4 for the velocity of the water. So by comparing them with Turner's, they are the same except for what? The deduction of 20%. So the same formulas. So he didn't state something new. Moving on, let's talk about Nocia. Nocia, he focused on something different that was ignored by Coleman and both Coleman and Turner's. So he focused his studies on the impact of flow regimes. So what do he mean by the impact of flow regimes? He followed a path for Turner droplet, but they made a difference from Turner by considering the impact of flow regime of the drag force ZD. If you remember, Turner took it as 0.44 in all the regimes, laminar, transition, and turbulence, which in turn determine the expression of the drag force. Hence, the critical equations, what will happen with them? So Nossier, in case he will be dealing with the laminar flow, he took the CD for 0.2 instead of 0.45. And in case he's dealing with or we are dealing with the turbulence flow, no, sorry, in case he's dealing with the turbulence flow, he changed it into 0.2, while laminar, he kept it the same. Okay, so according to the Reynolds number, if it's laminar, like if you remember, it's less than 2,300, he will take the CD 0.44 as Turner's, while if it is greater than 2,900, it would be turbulence flow, and he will take it as 0.2 the CD. So here you can see for the laminar flow regime and also for the turbulence flow regime, these equations. Okay, let's move further. Let's talk about Lee. Lee, it is the last one that we will discuss today for the models. So Lee, in his research posited that Turner and Coleman did not consider the deformation of the free-falling liquid droplet. So he's now considering something new. Other than the flow regime and other than the 20% deduction, he's considering something called the deformation. So in another word, he's telling us that the liquid droplet, it's may differ in its shape while falling, and assuming according to some velocities. So he contended that as the liquid droplet is entrained in a high velocity gas stream, a pressure difference exists between the fore and aft portions of the droplet. So the droplet is deformed under the applied force, and its shape changes from spherical to a convex beam with an equal side. So he means that first we have a spherical shaped liquid droplet, if you can see here at the end of on the slide. And here, according to some difference of the pressure between the portion, this liquid droplet can be converted, let's say, into a flat one. So spherical liquid droplet usually have a small efficient area and need a higher terminal velocity and the critical rate to lift them to the surface. However, the flat-shaped droplets have a more coefficient area and are easier to be carried to the wellhead. So he took into account the drag force equal to 1 instead of 0.44. And here you can see also the equation that he derived for himself also, and it is the function of interfacial tension and the densities. So till now we managed to talk about why do we have liquid unloading or how it will happen. We started with the stages of development. We talked in details about the third stage of the development where liquid starts to accumulate, and we somehow try to connect it and to tell you about what the flow regimes or the flow patterns happens in liquid accumulation. And we discussed the critical velocities and the models, the 4 models for Turner, the most common one, Nossier and Coleman, and the final one, Lee. So let us move further. And before I show you because we have some on Excel sheet, a practice that I gave from 2 years for the first 4th year student, I will tell you these few words before we start to show you about the practice in the Excel. So any well is unique. What do I mean by any well is unique? Each well have its own characteristics. So here, if we take into account this flow rate, critical flow rate that we took it from Turner, it is a function of a pressure, velocity, area, supercompressibility factor, and temperature. So each well have its own construction, have its own flow rate. The fluids model differs from one well into another. So here, if you want to calculate or predict anything, you have to have a data for the well. Not in general, we have to have its own data in order to continue with the prediction. So let's move now. Or let me try to show you the Microsoft Excel, the task that I gave from 2 years. Guys, do you see the Microsoft Excel?
No.
No. Okay, can you wait, please? Let us see how to. Okay, new share. What about now?
Yes.
Yes. So now we will talk or discuss what is the task that we did from 2 years. It's a very simple task for applied petroleum engineers, and it's quite effective one, and it's very useful. I know it's simple because we did only some, let's say, simple calculations. But from what I saw, it was very useful for the students because we talked about, let's say, a subject that is not discussed before, and which it was liquid unloading. So in our task, we took into consideration a typical gas condensate field that is located in Ukraine. And according to some production log, we took these numbers. So what I'm trying to tell you that these numbers that we took, it's a real gas condensate field. It's not from our own, like say, like mind or something. So we took into consideration numbers of well. If you can see here, everything in red, it is given. So here the number of wells, if you can see, it's more than 50 wells, or let's say around 50 wells. We took the data for 50 wells, and we had the wellhead pressure also for these 50 wells. So what did we do? We started by changing this wellhead pressure from bar into PSI. So one of the most common, let's say, tasks that is used, and to be a proper engineer, you have to know how to derive from one unit into another. So we changed this wellhead pressure from bar into PSI by multiplying it by 14.7. So here now we change it. So now what did we do? In order to predict the liquid loading, we have to take into account 3 models: Turner's, Coleman, and Lee. But back then, I only gave them only to Turner's model, and this Coleman and Lee, I did it by myself a few days ago, in order just to show you the what is the difference and to make it more clear for you. So for Turner's, we have to take the velocity of water according to his equations, if you remember. So his equation, it was 5.6, if you remember, and then we had to put the densities for the liquid and the gas, and then to divided it by the density also. So in general, we got the velocity of the water in feet per second, and also we got the velocity of the condensate in feet per second also. So here, what did we do also? We have to change them from feet per second into what? Into meter per second. So what did we do? We only multiply it by 0.304. So mainly we are just trying to change it from feet per second. So that's it. Sorry, from feet to per minute. So moving on, what is Coleman? Here, what did we do with Coleman? We took the same results from Turner's model, and if you remember, it's only the 20% that is difference from Coleman and Turner's. So we had only to divide it by 1.2. So we got the results also for Turner's, and it was a deduction of the 20% from Turner's, if you can see. And we took it in a very fast way. We don't have to make it in feet per second. We only took it in meter per second, which we need them. So here also we have for the velocity of the water for Coleman's model, and the velocity of condensate also for Coleman. And moving on to the third one, it's Lee. If you remember, he have his own equation. So we put the data in his own equation, and Lee, we only take into consideration velocity of water for Lee. So we change it also from feet per second, also into what? Into meter per second. So let's move further. And after that, we have to take the data, and it was given also. It was the tubing outer diameter. We have it in millimeter. So in order to calculate the actual flow rate or the critical flow rate, if you remember, it was a function also of temperature and area and pressure and everything. So something have to be considered first. So tubing diameter, we change them from millimeter into what? Into feet also by dividing it by 304. And from that outer diameter, we managed what to calculate for the area. And here we can see that it was a cylindrical area. So it's pi times area square divided by 4. So it's simple calculation. So now we have the area also. And here also we took another data that is given by them or in the production log. It was the temperature at the wellhead. So this temperature at the wellhead is in Celsius. So we had to change it also what into Rankine. So it is the temperature in Celsius plus 273.15 times 9/5. So we got the temperature what in Rankine. And if you're wondering, it is for all of them. And the specific gas gravity, let's say it was the same for all the wells. It was 0.624. Also, it was given. So here, if you have the specific gas gravity and the temperature and the pressure, if you remember in the first, here you can calculate that factor. And this that factor, if you remember it, we talked about it a lot in the classes, and it's a dimensionless factor. So it's 1 minus 5.5 times 10 to power 5 times the pressure. And then it would be the temperature, 1.3 divided by, sorry, the specific gravity, yes, to power 1.3, also divided by what? The temperature in Kelvin to 3.3 also. So here we have managed to calculate that factor. So if we have the Z factor, we have the temperature, we have the pressure, and we have the velocities and the area. Now we can manage to calculate the nominal flow rate, or let's say the critical flow rate, and to compare it with the actual one that is given inside the production log. And here, if you see at the end, this is the actual production log in 1,000 standard cubic meter per day. And here it's in million standard cubic feet per day. So these two results, let's say, were given, and they are the actual flow rates that we have to compare them with the nominal flow rate. So let's start with Lee. Lee also, we took into account, I guess now you will ask me why we took water instead of the velocity of the condensate. Because if you want to, let's say, compare the densities of the water and the density of the condensate, the density of the water is much higher than the density of condensate. So if the velocity of the water droplet is higher than usually the velocity of condensate, let's say, or if we took the critical velocity for the water, so if it's enough, then it surely will also will lift up the velocity of the gas. So of course we took water into account in these equations instead of the condensate. So here, according to Lee, we got these results. Also with the Coleman, we got these results. Also, we just put the numbers in the equation, if you remember. And for the Turners, also we had it. And one more thing, it was in 1,000 standard cubic meter per day we had it, and also we had it in million standard cubic feet per day. So we got two units that we're dealing with. So here, if you can see that we got all the results for all the models, all the three models right here. And we have different results, of course, because we have different equations. So if you want, let's start to compare the first result with the actual one. Since the actual flow rate is greater than the nominal in Turner, in Coleman, and in Lee, so the liquid will be able to lift itself, liquid droplet will be able to lift itself to the wellhead and then into the production facilities. So we don't have any liquid accumulation here. Everything is good. The well is keeping on flowing, so nothing bad. Here, if you can see, we have the actual flow rate. If we want to compare it with the nominal flow rate, for example, in Turners, we have 52 and 35. So the liquid flow rate, the critical flow rate is much higher than the actual flow rate. So we will have the liquid accumulation. And also in Coleman, we have 44. So it's also higher than 35 in actual flow rate. Also, we will have liquid accumulation. And in Lee also, it's 43, that it's greater than 35. So I guess you can see what kind of the approach we're talking about here. So in general, if the nominal flow rate is much higher than the actual, then we will witness liquid unloading. And if it's opposite, if the actual flow rate is higher than the nominal, we will witness what a normal flowing well. And here, if you can see, let's compare the results. The results for Lee model are the same as the results of Coleman. You can see I put the Lee results in yellow, and this let's say orange for Coleman, and they have the same, not the same result, but they are quite very similar. And in these cases, they have the same result. What do I mean by the same result? That the actual conditions are enough to lift up the actual flow rate is enough to lift up the droplets. While if we want to talk about Turner, we have only 6 wells where the actual conditions are enough. While in Lee and Coleman, they have what? 9 wells. Yes, approximately 9 wells. So Turner, I'm not saying that Turner was more accurate than Coleman or Lee, but at the end of the day, they are just numbers, and we have to take into account that it may be different than the others while comparing them with the lab experiment, the results. So what I'm saying that, okay, like we are sure that for 6 wells, the velocity is enough to lift up the liquid droplet, and the others are not enough. So we have to compare them also with the lab experiment results. And one more thing, if you, in case that you're wondering why I didn't take into account the Nossier approach here, because simply back then we only had to compare Turner's model with the actual model. And like I stated before, today that it was a couple days ago that I did by myself for Lee and Coleman. And if you remember, Nossier, he was talking more about the flow regime. So here, when I took the numbers, I didn't know which flow regime to take into account. So I didn't want to compromise the credibility of the study here. So that's why I didn't have the viscosity, and I didn't have the temperature back then. So that's why I didn't put Nossier approach here. Okay. So at the end of this task, we managed to know which wells have enough condition, actual enough condition to lift up, and which well will undergo what? Liquid unloading, and they have to be routed into solving this problem by artificial lift methods. So let's go back to the Microsoft PowerPoint. I guess we are reaching at the end of our lecture. Do you see the Microsoft presentation now?
Yes,
Yes.
but not full screen.
Not full screen, sorry. Now it's full screen, I guess. Yes. So, like we stated that any well is unique, and we talked about what do we mean by that. And if you remember, I told you it was from 2 years that that task that I gave to my students back then. And this is the table that we got, if you remember, only for Turner's model. We discussed it in details in the Excel sheet. And here, when we had this sophisticated, let's say, softwares, we also managed to calculate for some typical wells the liquid unloading, if we have liquid loading or not. And we take into account some actual flow rate and critical flow rate. And here, if you can see that we have the actual gas velocity and we have the critical gas velocity inside the pipe seam. And if you want to compare this value with this value, we can see that the critical gas velocity is higher than the actual. And if you remember, if we have the critical is higher than the actual, then actual velocity is not enough for the liquid to be unloaded. And here also you can see the actual gas velocity with the critical gas velocity. If also we want to compare them, also we can see that the actual gas velocity here is enough, and it's higher than the critical, so is enough for the liquid to be unloaded. So here it's only 3, we took into account only 3 wells, and from the bottom to the tubing and alongside the tubing. So I'm just telling you like the difference in Excel and in pipe seam. They have the same results, only in Excel it will take longer time, while in PipeSim, let's say life is more easier for such things. And at the end, if we are dealing with liquid accumulation, what should we do? We have to deal with such problem by liquid unloading methods. I will not talk about liquid unloading methods because since my colleagues already discussed it in details and they showed, let's say, very interesting videos. I'm sorry, I don't have videos. I don't have cool data to share it with you guys. I'm just trying to give you the basics. So liquid unloading methods. So what do we have? We have ESP, electric submersible pump. We have plunger lifts. We have tubing changing also. We have gas lift continuous, and we have gas lift for periodic. We have capillary foaming, coil tubing, also rod pumps, and etc. And in case that you will ask me about how can we choose, it depends on some screening criteria, like for choosing the optimal liquid unloading methods. What do I mean by screening criteria? We have, like, in general, it's divided by 4, like it's for reservoir, for well, for economic, and others. What do I mean by reservoir? Like, for example, the temperature, the pressure for the well, the fluid types, the viscosity, the solid contents, the water cut, a GOR, oil gravity, for example, the bubble point. And well, it depends on the location, the geometry, the diameter, the depth of the well also. And economic investments and how much it will cost, operating cost and service cost, and etc. So unfortunately, no matter how the idea is great and brilliant, if it's not economically feasible, then it will not be taken into consideration, because at the end of the day, we're living in a world where if your idea will cost too much, then sorry, we cannot implement it. It's all about money. It's all about revenue, how much we can get. So yep, economic plays a big part. So in few words, the screening criteria, how we can choose the best liquid unloading methods, it depends on some criteria that I just explained for you. And at the end, thank you very much. Again, my name is Алі Чкеїр, and I would be glad to answer your questions if you have.
Okay, I have a question, Ali.
Yes, Anastasia.
You calculated liquid loading in PipeSim, right? And which model did you use there? Turner?
We used the most common basic one, Turner's.
Okay, thank you.
Пожалуйста. Guys, if you have any questions.
But you didn't compare with others, right?
In the PipeSim, no. No, I didn't. No.
And carrying out in PipeSim, how long did it take you to like input the data and all that and achieve the results?
In PipeSim, it's very fast.
Very fast.
Yes, because in this Excel, you have to put, like, for each and every one. In PipeSim, you only have to put like data. Nastya knows about it more than me. Like, it will have, you have to put 3, 4, 5 datas, and you just put simulation or run, and they will give you everything like in seconds. We're living in a very advanced world.
But before you need to...
Let us be honest, not in seconds. Sometimes in minutes and sometimes in hours, I guess.
Well, I guess I was lucky back then.
Uh-huh.
But data preparation is really important there. It's not like you can put just like numbers and it's all.
Well, sometimes for the production engineer, if everything is prepared, he only have to put just enter and to run the simulation.
The thing is, Anastasia, Ali used corrected data, and this data was analyzed before, and some, I think, some abnormal values was taken away from his research, because it was given to him like pure data for some testing. In the case of production company, to choose the wrong data means that you will get wrong results. And in such case, every time with any sophisticated software, you have to work as a team. If we talk about pipe theme here, this team must include PVT reserve engineer and I guess some guy from production facilities. And moreover, everything depends on the well testing, how good well testing is done and how we can predict some situation. Moreover, if you accomplish something even in good software, you have to feel your field and know that the results that you will get will be correct one, but not some kind of unexpected. But it's really good, Ali, to present your research. It's like different point of view. As for me, it's quite good for the students to know the basics, why liquid could float
Yes, this is
vertical pipes and horizontal pipes, and that anyways, the same forces are working.
No, this is why what I was trying like to tell these guys the basic principles and such things. I can see Ali Dilbani ask me, is it helpful or not in the pressure, when the pressure we have low pressure? If you remember, Ali, when I was talking about Coleman, I put a conclusion for Coleman that his approach, it is the most suitable one if you are dealing with a wellhead pressure that is less than 500 psi. So Coleman showed a very interesting, let's say, promising results, taking into consideration the low pressures when we are dealing with wells with low pressures. Bolatsi, do you have any questions? Because I always know that you have too many questions.
I was trying to be considerate.
It's okay, we have time.
Okay. In your own opinion, do you think those other models that they developed like as alternatives to turners are actually useful anyway, or we just stick with using only turners, like the Lee, the Coleman,
Well, usually if you want to search on internet, because like what I usually do if I want to prepare something for liquid unloading, I search on internet, and it is the most common models that they are used, and these are the common approach. You understand? Because in Lee, he introduced something new with the deformation. He told you that, okay, the liquid droplets is changing, you understand? While in Nocia, he told you, no, let's talk about the flow patterns. So these people are discussing everything that's new. So if you want to open any research on Google, and you can see in SPE papers or all around the world, if they want to talk about liquid unloading, their introduction, first of all, they have to mention Turner. This is for sure. This is 100%. They have to mention Turner because he was a co-founder. And somehow they are trying to improve it. You understand me? What do I mean by improve it? They are trying to manipulate, to start to change a little bit of the numbers. But let me tell you, the approach is the same. They are just trying to change the coefficient by a little margin. But in general, yes, these four models are the most common ones.
All right, thank you.
Mm-hmm.
The one more thing, Ali, if you will get back to the slide with patterns of the flows, it was slide number 3, I guess. Can you get back?
Yes, let me. Wait a little bit. This one, right?
Yes, and here it's quite good to see what could happen with and how the different flows could be obtained. Usually, to be honest, if we turn this graph from its head to its leg, it will be much more better, because if you imagine that at the well bore each some particular volume of liquid starts to create some slug or create some volume. This volume will be taken by the gas, and first of all, it will move as the slug, but with the pressure dropping, it was like a little bunny asked, what happened when the pressure dropping, or is it good for us if we have deal with low pressure? This slug of water, which is, or any other liquid which is moving up, starts to be broken on some parts of this slug, which is charmed then, and up to the wellhead, this charm will create a little charness, which is like a mist in gas. It's only because the pressure drops, the velocity will increase, and every time, it does not mean that you will have deal with the same pattern on floor along all the tubing. It means that at wellbore you can have deal with a slug and plug motion. With charm floation somewhere in the middle of the tubing, and up to the wellhead you will get back to the annular or a mist flow. But the calculation of any calculation or any formulas or any such simplified models show you all the liquids in tubing. So it doesn't mean that this volume will be located on the wellhead. It is all the volume of liquid from wellhead to the wellbore, but in different patterns. Did you understand me?
Yes.
Mm-hmm.
Here he was trying to correlate it mainly with the velocity. Like we started with a high velocity, so we had this annular and we had the film flow pattern, annular mist. And then when the velocity starts to decrease, we start to witness the churn, the slug, because it is unable to lift it up by itself. And then unfortunately we have this bubble at the end, which is the lowest gas velocity, let's say, or liquid velocity that cannot, that will accumulate inside near the sand face.
Exactly. That is why when we try to predict liquid loading on the wellhead, we will put the pressure. We have to put the pressure at the wellhead, at the wellbore. That is why any model, including Turner model, recalculates your pressure on the wellhead to the wellbore pressure, and if the wellhead's velocity will be enough to move liquid, it means that the wellbore velocity will be enough to move the liquid. It means that at the wellhead you will have enough velocity also.
True.
Yeah.
Very true. Hisham, you don't have any question because somehow it's related to your research. Well, I guess no further questions.
No, I don't. To be honest, I need to listen for it and another time so that I can like understand everything you said again. You know.
I hope I wasn't that fast.
No, but like I need to read like every slide because like I didn't read exactly every slide, and I need to read it so that I can understand it really good. But it was really a good lecture, though.
I can send it to your email. The presentation.
Yes, if you can, please.
Yes. Mikhailo, I guess we finished for today, right?
Yep, we're finished for today. So we are waiting for next week. Next week we will have this midstream week mostly. So oil processing, natural gas processing, crude oil processing, natural gas processing, compression equipment, as well as on Friday we will meet with selectors with the lectures dedicated to reservoir engineering and reserve assets.
And I have to ask you, did you Did you enjoy my story? It was accurate, how I met you.
To be honest, Ali, at that time when you start with your story, I started to speak on the phone and switch on.
So you didn't hear the story.
So I did not hear it. It will be a surprise for me. I will listen to this on YouTube channel.
Okay, then.
So take care, guys. Have a good day, and we will see you next week.
Okay, guys, stay safe, and Ramadan Kareem for those who started today.
Bye.
Goodbye, guys.
Bye-bye.